Okay, so this is the solution to problem number 5, dealing with the backpacker. So, I'll write number 5 up here at the top there. And, let's go with the less angry color. Let's just go with, I don't know, a little blue. All right, so you might recall that I talked about if you have a track, all right, and you run around a track right here, and here's your start point and here's your end point. All right, and you go all the way around the track, all right, and back to the beginning right there. You've run some distance. Your distance is what's the distance of a track? Is that equals 400 meters, right? Or 400, yeah, 400 meters. But your displacement, we'll call that your delta x. Now, don't be scared of that delta. That's a Greek symbol that means a change in. All right, so your change in displacement. Your distance is 400 meters, but your displacement is your location. You really haven't changed your displacement because you arrived, after the whole trip, you arrived back at the exact same point that you were originally. All right, so the difference between these things, change in displacement being 0 meters, is that distance is what we call a scalar quantity. That means you walk, or you run, around this track. It doesn't matter what direction you're going. You just keep adding up meters that you are accumulating. Okay. What this displacement here is not distance, or sorry, it's different from distance. It's not a scalar quantity. In fact, I'll write that in here, scalar. But what displacement is what's called a vector quantity, and maybe you've already been taught about that. Vector. All right, and usually you see vectors with little arrows over them. That's a little arrow over the character right there. And the reason that this is this all adds up to 0 is because vectors are a certain value that is a certain distance, but the direction that it's in is very important as well. So I'm going to change to red right here. If we add up that distance in that direction, and that distance in that direction, and this distance, which is it's the opposite direction as this, right? They're opposite directions. So we'll call this positive, and we'll call this direction negative. So positive, and actually, you know what? I'm kind of doing this backwards right here. Let's call this negative, all right? And that negative, and that positive, and this positive. All right, what happens if we add up all those values? So we'll say -1 plus -1 plus +1 plus +1. You wind up back to 0, okay? So displacement and velocity are vector quantities. And so the point here is that the direction that it's in is going to be very, very important, okay? If that doesn't make sense, don't worry about it too much. It's just a little kind of I'm trying to move that around. I'll undo that right there. I'm trying to shrink that down and move it. I'll just leave that up on the corner right there. All right. Now let's apply the idea of a vector to our hiker. Okay. So our hiker starts here. Okay, and we are told has an average velocity towards the west of 1.33 meters per second. Okay, so that's the average velocity. Now I'm not going to write the value in right there. That should be a V. Average velocity. And then, in fact, we'll write that down below here. Average velocity equals 1.33 meters per second due west. Okay, direction is very important here because what we're going to see is the values in the west direction are going to be, let's just say if we call that positive, all right, positive 1.33 meters per second. Then anything in the east direction we have to regard as negative, just like our track up here. All right, if we start out negative and then we go the opposite direction, that's positive, which is why all this stuff adds up to 0. Okay, so we're going to keep direction in mind right here. Let's see if I can delete this little thing down at the bottom. I can't. I'll just leave it. Sorry. Okay, so on average, she walks from here to here. All right, we'll make a little red dot at the end to show that's the stopping point. Okay, just like this person on average went around the track some distance, but on average the velocity was 0. It's like they wound up in the same spot. They didn't really go anywhere. Okay, so anyway, now did this person really just walk from here to here? No, they walked, what is it? They say in order to do this, or the question says this average velocity results from her hiking 6.4 kilometers, and I'll do this in green actually so you can see that these kind of add up to that average velocity. 6.4 kilometers, so we'll call that velocity 1. 6.4 kilometers to the west with some velocity right there, and then turns around and then hikes at some velocity east and winds up at the same point right there. Okay, so we're going to call this velocity 2. Velocity 2. So she goes all the way out here, turns around, and then comes back. But it's just kind of like saying that if she were to just go from here to here on average. Just like right here, this person goes all the way around the track, but they make just as much progress as if somebody were standing here the whole time because they wound up at the same spot. I hope that makes sense. Okay? So, let's write down everything that we know. Okay? Velocity 1. Velocity 1, that is to the west, that's that longer green arrow right there, equals 2.57 meters per second. And that's positive, right? We're gonna call west the positive direction because that's the direction that she's starting out. All right. So west, east. We're gonna call east negative and west positive. Okay. So for that first leg of the journey, she had a positive velocity of 2.57 meters per second, and she also had a distance, that is, she hiked for a distance of 6.44 kilometers, right? Now, there's something we need to fix with that real quick, all right? Look at those units right there. This is meters and this is kilometers, so let's make all of our units the same, so everything is kind of this in a standard notation. We got 6.44 kilometers. What is that in meters? Well, a kilometer is 1,000 meters, so that would be 6,440 meters. Okay? And actually, you know what? I'm sorry. I messed something up right here. This should not be D1. I should really be calling that. Let's see if I can zoom in there. Oh, I'm moving it all around. Darn it. I should really call that, instead of distance 1, it should be delta x 1. And I have a hard time moving. I've got a menu bar in the way. I can't write that. I can't write that that little triangle in front right there. In fact, I'm going to shift that over so maybe I can. There we go. Delta x1. Because direction is going to be very important right here. I drew that little arrow over the x kind of like I did over here, right? Because velocity is a vector, and I should have written an arrow right there. Okay, velocity is a vector and displacement is a vector. We're going to be more concerned with displacement than we are distance. Okay, because if she wants to go from here to here, she could go all the way out and then come back, or she could just, on average, walk here and walk slower and wind up at exactly the same spot. Okay, so her displacement is 6,440 meters to the west. Okay, now let's look at velocity 2. Velocity 2 is that second leg of the journey right here. All right, velocity 2. And I'll put an arrow over that because it's a vector quantity. It's direction dependent. Velocity 2 is, what was it? 0.465 meters per second to the east, right? So if direction is important right here, then what I need to do is I need to put a minus sign in front of that. Okay, does that make sense? Now, it's true that you can't walk minus 0.465 meters per second. You can't walk in a negative, you can't walk a negative amount. But since direction is important with vectors, we're going to call that a negative quantity for math purposes. Okay, she's going in the negative direction at 0.465 meters per second. What we don't know is so in part 1 right here, we don't know the change in time. Okay, and in part 2, and this is what makes it kind of confusing, or not confusing, but a little more difficult, we don't know the change in time 1, change in time 2, and we also don't know the change in displacement for part 2 as well. And by the way, that's what we're solving for right here. Okay? So why would it be, when I was originally going through this, I was saying, we're missing something. If we knew this time right here, it would make it really easy to solve for the second displacement. All right? Or if we knew this time right here and the average time it took to go from here to here, this distance, we should be able to solve for it. But I was originally saying, we need more information, but actually we don't. Okay, we don't really need more information. What we can do is we can solve for this second leg of this journey, this delta x2. I should put an arrow over that because it's a vector. We can solve for that by doing what's called substitution. Okay? So let's go back up to this first time right here. All right, this first time 1, we actually can solve for that. All right, that's this right here. We can solve for that and get a value for that because we know that velocity, where can I write this if it's not in the way? Velocity equals a change in displacement over a change in time. All right, displacement is a vector and velocity is a vector. So for velocity 1, we do have a velocity and we do have the change in displacement. We can solve for time, right? We can solve for time 1. We cross multiply, right? So the time is going to come up to the top here and velocity is going to come down below. So we can really say time 1 really is going to equal change in displacement 1 over velocity 1. Does that make sense? All right. So let's find out what that is. And I really wish I hadn't taken up all the space right here. What is our change in displacement 1? Well, we're told that 6,440 meters, okay, over what's the velocity that she originally walked with? 2.57 meters per second. All right, and that's going to give us the amount of time that she took to walk that first leg of the journey. All right, now it may not seem like that's important, but it is. It is going to be important because we're going to need to do that to solve for this second displacement right here. Even if we don't know the second time, that's all right. All right. So let's find out what that is. So if we take displacement 1 divided by velocity 1, we get, I'm going to round this, 2,506 seconds. Okay? So that's like, I don't know, 2/3 of an hour. All right? Like 45 minutes or 40 minutes, something like that. Okay? That's going to be important to us. And we can solve that because we do know the velocity 1 and the displacement 1. Okay? We can't do that here. We can't do that for part 2 because we know the velocity, but we don't know the time and we don't know the displacement right here, but that's okay. Because here's our assumption. All right? The velocity, I'm going to write this in black and this is going to be important. The average velocity for the whole trip, I'm going to write TOT for total. All right? And we're given that. Right? We're given that at the very beginning. That's this right here, this blue one. The average velocity for the whole trip is going to be displacement 1 plus displacement 2. Those are vectors right there. Divided by time 1 plus time 2. Again, those triangles mean change. All right? Any elapsed time is a change in time, right? And displacement is simply your change in location from where you started to where you ended. Okay. We're given this right here. We are not given. This is what we're solving for, right? Our displacement 2. That's what we're solving for ultimately. In fact, I'll circle that in red. That's what we really want to solve for. And let's see. We just solved for this change in time 1 right here. But this right here, that's the bugger that, man, if we knew that, that'd be easy because we would know that, we know that, we know that, and we know that. We could solve for our displacement 2. We can't do that because we don't know the time, but that's okay. Because we know, like I said before up here, look at this. If velocity, or think of it as speed, all right? Velocity is your change in distance over your change in time. We can say down here look at part 2, all right? We don't know that. We don't need to know that. That's all right. If we say, okay, our velocity 2, let's not write that in. Now let's write it in red. Okay, velocity 2 equals our change in displacement 2 over our time 2. All right. If that's the case, then we should be able to turn this around and solve for time 2, right? We should say, all right, well, just like we did up here, time 1 is displacement over velocity, right? So if we turn that around and our displacement, our change in time 2 equals our displacement 2, which is what we're solving for, divided by velocity 2, we have an expression for that time right there. But you're saying, well, wait a minute, we don't know this, and we also don't know this because this is what we're solving for. That's all right, because if we take this time 2, oops, and let's write that in here, and we stick that in there, we go from having 2 unknowns, we don't know that, to not knowing that, to 1 unknown. And I'll show you why that is. I'm going to write this equation at the bottom right here, and then I'm going to take another page to actually solve that equation. Okay? So this is our major assumption. The total average velocity is the sum of the displacements over the sum of the times. All right? Total displacement over total time. The total average velocity. If we take this and stick that in there, here's what we get. Let's write this in black too, because this is going to be important. Average velocity for the total trip equals change in displacement 1. Got it. Plus change in displacement 2. Solving for it, right? Over change in time 1. We solved for that, right? We figured that out up here because we knew the displacement and the velocity for part 1. Plus, and here's the big deal right here, plus we stuck this and substituted that in there. So this is going to stick in there. Plus, we're going to put that whole fraction in there. Change in displacement 2 over velocity 2. Okay? This is going to be the big deal that we just achieved right here. Do we know average velocity for total trip? Yes. Displacement 1, yes. Displacement 2, we're solving for, right? So we don't know that. Do we know time 1? Yes, we figured that out up here. Do we know velocity 2? Yes, we do. And displacement 2, we are solving for. Now, the funny looking thing about that is the fact that we've got our unknown. It's both the same unknown, but we've got our unknown in 2 places. That's okay. We're going to use algebra to combine that into one place so that you can solve for it, okay? But the good news here is that we went from 2 complete unknowns. We didn't know that, and we didn't know that, and we used what's called substitution. We wrote a statement about time 2 in terms of displacement 2, so that when that got stuck in there, we went from this unknown to being an unknown that has the unknown in it that we're solving for. All right? So let's go to another page right here, and I'm going to solve for that. All right, so up again at the top. Average velocity for the whole trip is displacement 1 plus displacement 2. That's what we're solving for. Okay? Over. In fact, I'm just going to put T1 because change in time 1 is any amount of time is a change in time, right? So that seems kind of redundant. I'll simplify it a little bit. Just call it time 1 plus this fraction. Displacement 2 over velocity 2. All right? Now, we know everything except for that one thing that we're solving for right there. That and that. We just need to get them all together. Okay? So, that's our main assumption going into this right here. Let's see if we can combine those delta 2's, those change in displacement 2's, and so you have something to solve for, okay? All right, first thing I'm going to do is I'm going to take all this mess down here in the denominator, and I'm going to multiply it up. All right, so we don't have this fraction over here. I'm going to multiply it up so that this whole T1 plus this fraction comes up and is multiplied by the average velocity on the left-hand side, okay? So it's going to look like this. Why am I writing in blue? You know, I'll stay with blue. All right, this is our main assumption. Blue is going to be our crunching numbers color. Average velocity times T1 plus delta x2, that's what we're solving for, over velocity 2. Okay? Equals. All that stuff came up, so we just have delta x1 plus, that's a plus sign there, delta x2. I think I got that right. Right? Oh, that's a vector. That's a vector. Let's just keep our vectors right there. Okay. We'd love to get these delta x2's together, right? Because that is the only thing that we don't know. We want to somehow get them together. That's going to be really hard because it's stuck in this fraction right here, added to this t, inside this parentheses right here. We need to kind of free this delta x up. So let's kind of break open these parentheses by, let's distribute this average velocity to the t and to this fraction right here. It's going to get messier before it gets cleaner, but that's all right. Go back to blue here. So let's distribute the average velocity. So we got average velocity times time 1 plus average velocity times this whole fraction. In fact, I'm not even going to put the parentheses right there. Average velocity times delta x2 over velocity 2. All right, see what I did? I distributed the average velocity to the t1 into that fraction right there. If you multiply it by that fraction, it really just goes up in the numerator, right? All that equals delta x1, displacement 1, plus displacement 2. By the way, you may be noticing that we're not dealing with any numbers quite just yet. It is much easier to rearrange, you might say, variables than it is to rearrange numbers, especially when you start plugging numbers in and getting things mixed up. We're going to completely rearrange this to solve for what we want and then plug our numbers in at one time at the end. Okay? All right. Again, what are we solving for? We're solving for that guy and that guy. In fact, we want to mash them together into one unknown. So, let's get them both to the same side of the equation. All right, let's get them both to the left-hand side. So this guy is going to stay where it is. This guy, how are we going to get it over there? We're going to subtract it, right? Subtract it over to that side. And this guy, we're going to get rid of it because there's no delta x2 in there. We're going to subtract that to that side. So these guys are basically going to change locations and have minus signs in front of them, right? So we're going to have then average velocity times our change in displacement 2 over our velocity 2. And remember, this got subtracted over, so we're going to say minus delta x2 equals our good old delta x1 that's been sitting here this whole time minding its own business. Delta x1 And then this guy got subtracted over to that side, right? So minus average velocity times, I should really put that in a bracket right there, minus the quantity, average velocity times time 1, right? Now you would have done the multiplication first anyway, because that's order of operations, but that maybe just kind of combines it there a little bit. Okay. All right, let's ask ourselves, what are we solving for? We're solving for these guys. They're getting closer together, right? All right, what can we do now? We can do one thing to get these two delta x2s, which is what we're solving for, into one delta x2. What can we do? We can factor them out. We can factor them out and put them out in front of a parenthesis so that everything else in here is in brackets. So it's separated out. So it's going to look like this. Delta x2, our change in displacement 2, is going to come out front, and then everything else is going to be in brackets right here. So that's going to be average velocity over velocity 2 minus what does this become? It just becomes a 1, right? Because that's just a 1 minus 1 equals delta x1 minus average velocity times t1. We're getting a lot closer. Look at this. We went from two unknowns, well, to our unknown in two places, to our unknown in being in one place right here. Now it's gotten a lot cleaner. All we need to do is get everything else away from it so that we can solve for it. All right, so what's the last step we're going to do? In fact, see if I can move this stuff up. Oh, no, I can't. All right, well, it's going to move all kinds of things individually. That's going to be ugly. What can we do to get just this by itself? We're going to take this whole mess, this whole thing inside the parentheses, and just divide it down below here, right? Divide it so that it goes away on the left-hand side and it appears in the denominator on the right-hand side, okay? So if I can squeeze that in at the bottom, we'll have a working equation to solve for the displacement 2. Delta x2 is going to be equal to delta, I'm really going to run out of space. You know what? I lied. I'm going to move this up to the side. I'm going to move this up to the top right here. All right, I like when everything is in one nice big tall stack, but it's just not going to be feasible right here. I need some vertical space. So we're going to say delta x2 is going to be equal to change in displacement 1 minus the quantity average velocity times t1, right? That's a time sign right there. All over average velocity over velocity 2. Now that's a fraction right there, all right? So I'll put little brackets in there. Minus 1. And that's our denominator. We now have a working equation that will solve for your displacement 2. All we got to do now is just what we said, we just call it plugging and chugging, right? Plugging our values in because we know all this other stuff. And we have an equation that is set up to solve for our delta x2. So, assuming you do your order of operations right, here's the values that we're going to plug in. So delta x, why is that red? Oh, because I was using red last. Let's do it in blue. In fact, now I'm not even going to do it. I'm going to do it in black because this is what we actually want to plug in here. Our delta x2 is going to be equal to, what's our initial displacement? That is 6,440 meters minus the average velocity for the whole trip, 1.33, times, what's the time? Time for part 1. That was, I forget already, 2,506 seconds. All right. 2506. And that's a time sign in the middle right there. I'm not going to put my units in because I ran out of space. But you would probably do well to write your units in right there. Right? Over this big quantity right here. What's that first fraction we have? Average velocity, that's 1.33 meters per second over, what's the velocity 2? All right, this is going to be important. Remember, our velocity 2, it was not 0.465, but it was negative 0.465 meters per second minus 1. It seems like kind of a simple way to end right there, but it's minus 1. That's just what the equation is right there. Putting this minus sign in here is gonna give us a final displacement in the correct direction. It will be in the negative direction, because remember, this is the displacement 2 is east, right? And we said east is negative. So let's plug our values in and see what we get. What I get, and I'm not gonna key it all in for you. You can do that. But here's what I get. I get a value of our displacement 2 is negative 805 meters. We solve for that right there. Now remember, you can't walk a negative distance, but you can walk a negative displacement. You can walk a positive distance in the negative direction. And since we considered east, that's really east, right? East we consider to be the negative direction. That makes sense that our answer is negative, because we're going kind of backwards. If we go back to the original problem right here, she walked positive and then she walked backwards right here. So that's why the answer is negative. Or you could say she walked 805 meters in the east direction, which is negative. Either way would be correct. So I went over my problem a couple different times. I think I got it right. But I make mistakes too. So maybe I did a little math problem right, or math error right there. But that's how we solve for problems like this. Going back to one, we went from having two unknowns. This unknown, oops, I don't want to do that. This unknown and that unknown, to only having one unknown, because we substituted in a statement for that second unknown that is in terms of the first unknown. Now, it resulted in us having kind of a messy algebra equation, because that one unknown was in two different places. We mashed it all together by doing some messy algebra. Finally having a statement for that single unknown right there, delta x2, and now we have a final answer for that single unknown. So there you go. That's physics and algebra, or we sometimes call physics applied math, really applied algebra. And there's your answer to problem number 5. So hope that helps. Let me know if you have any questions. See ya.